Good evening, everyone. Thank you very much for those of you following us online today. And it is our 11th time to conduct the Meet the Author webinar. And today we have pleasure to invite Mr. Robert Massus, and who is the author of Changing It. This very one of the bestseller book, both online and also offline, and it also published in many different of language. So both including traditional Chinese version and of course the Mandarin, the simplified Chinese as well. So today it's our pleasure, and it is really great to have you with us. So Robert, if you are ready, the floor is yours.
All right. Thank you very much for that, Hung Yi, and hello everyone. And thank you for making time to listen to my talk, which I have focused on the issues of financial science and the way that probability and statistical issues affect that. So let me make a start. Okay, hopefully everyone can see that.
Yes, no problem.
Good. Okay, so what I'm going to be talking about today for the next sort of 35, 40 minutes or so are what I see as three dangerous beliefs in statistical, concerning statistical science in finance, which is a field you're all particularly interested in. So, come on, why is it not? Okay, so a little bit about me. So I started out with a degree in physics from Oxford University, and then I went into science journalism and worked for many different newspapers and magazines over the last 25, 30 years. These are just some of them. And I've also written a number of books, and the one that Hung Yi was gracious to mention was my latest book, Changing It, which is all about the laws of probability and how they affect your life, and how, if you understand them, they can change your perception of how the world works. So one of the things that I picked up as a result of working for national newspapers for many years was the way in which so many news stories are backed by statistical evidence, from clinical studies claiming that a new drug is very effective, or indeed doesn't work as people thought it did, and also that people who do things like live near electric power lines may be more susceptible to cancer, and then other studies would appear saying, no, our study doesn't show that. And after some years of studying these, reporting these studies, I started to wonder why they never seem to converge on a reality. You know, either there is a risk or there isn't a risk. The drug works or it doesn't work. And for me, I was sort of brought up to believe that science bit by bit converges on the truth. And I was perplexed by this phenomenon that I kept reporting stories for like 10, 15 years, where you're thinking, are we ever any closer to the truth? And that made me become increasingly interested in the way that we draw conclusions from evidence, which is statistical inference. And as the years have gone by, I've moved increasingly over to academia and have started doing academic research in basically looking at this problem of why statistical evidence doesn't seem to converge to a truth, whatever that might be. And so I've now got a dual career, both as a writer, a science reporter, and also as a visiting professor in statistical inference at Aston University in Birmingham. And I've written a number of papers outlining my techniques for trying to overcome these problems that standard statistical inference technique seems to have with converging on the truth. So that's what I'm bringing to today's talk, and in particular, applying it to statistical science and the issues that can emerge in finance. Now, to be fair, I know that you might think I'm picking on finance here, but the fact of the matter is my sort of 20, 30 years of being immersed in various fields of science has taught me to recognize that these three dangerous beliefs are also common in medicine, in psychology, in ecology. They are everywhere, and they are having really bad effects on our quest, our scientific quest for the truth, for want of a better word. So let's look at the first of these three dangerous beliefs, and it centers on this, which you'll all recognize. It's, of course, the bell curve, or the normal curve, or the Gaussian distribution. It goes by various names. And the first dangerous belief I want to discuss is that normality, that things following the normal curve, is the normal way things behave. Now, cast your mind back to the global financial crisis of 2007, 2008. This guy was front and center of the early days of that crisis. His name is David Viniar, and he was until recently chief financial officer of Goldman Sachs. And during the early days of the global financial crisis, he emerged from Goldman Sachs offices to tell a journalist that they were going through just astonishing times. And this quote became part of the public record. We were seeing things that were 25 standard deviation moves several days in a row. Now, I'm not sure whether the journalist fully understood what that meant, but certainly the quants, the quantitative analysts at Goldman Sachs, certainly knew what it meant. And it is an absolutely extraordinary statement, because basically when you put it through the machinery of the normal curve, it turns it into a probability. So typically, now, if we're used to seeing prices move by about one standard deviation a day, that's nothing particularly impressive. For us to see a 25 standard deviation move, you would have to wait for about 10 to the 135 years to go through several days of that, which is like never. In fact, it's the closest to never I can think of, because the universe is only 10 to the 10 years old. So it's, you know, it's many, many lifetimes of the universe. So it's clear that this guy was saying in a quant sort of way that these were extraordinary times, and Goldman Sachs had been incredibly unlucky. But was he? Just how lucky was Mr. Viniar? A number of people pointed out not long after he came out with that quote that really what that's saying is not that you've been unlucky and that you've been hit by a very low probability, astonishingly low probability event. It actually means you're using the wrong models. In other words, you've based that calculation for turning a standard deviation move into a probability using the wrong probability distribution. But I would still argue that Mr. Viniar was very unlucky, but just for a different reason, and that is he was the most famous person to come unstuck as the result of the work of these two Victorian mathematicians, Adolf Ketalay was a Belgian mathematician who became fascinated with the bell curve and started to believe that this mathematical entity could apply to many things in everyday life, like the heights of human beings, that they followed a normal distribution. And he did some work to show this. And Francis Galton, an English mathematician, and many other things besides, also became fascinated with the apparent ubiquity, the universality of this normal curve, that it seemed to fit all sorts of different things if you didn't look too carefully and weren't too fussy. And it was Galton who started to call this curve, which some called the Laplacian curve or the Gaussian curve, it was Galton who called it the normal distribution. And that created this impression that it was just the normal thing you could expect to see in many circumstances. Now, what's the basis of that belief? Is there any real basis for the idea that the normal curve really should apply to loads and loads of things? Well, yes. As a result of the work of this guy, the French mathematician Pierre-Simon de Laplace, who came up with an absolutely brilliant discovery, which goes by the very boring title of the central limit theorem. And that basically says, in non-mathematical language, that if you have enough random influences all working together, their combined effect of any type of random influence, you don't have to know the nature of it, implies that formula, that probability distribution. In other words, the bell curve. It's an extraordinary discovery. And given that it applies to any type of random influences, you don't even have to know what they are. Well, the normal curve would seem to apply to price movements too, right? Why shouldn't it? I mean, we've talked about it applying in such general circumstances. But wait, is it really any type? In fact, there are, as with all statistical theorems and theorems in general, there are some terms and conditions, and these are often ignored. What are they? They're these at the bottom in small print, like all terms and conditions, that the random influences must be independent and have a finite variance. Now, when Laplace originally proved it, he had an extra condition that they had to be identically distributed as well as independent and have a finite variance. But in the early 20th century, in the 20s, this guy Lindeberg relaxed, showed that one of these assumptions could be relaxed. So it's very, very general. But those are terms and conditions, and we have to be sure that what we think should follow a normal curve obeys those terms and conditions. Otherwise, we could be in trouble. And the fact of the matter is that normality is nice. It's got lovely mathematical properties that we needn't go into today, but it allows a lot of analytical results rather than mathematical or computational results rather. We don't need a computer to do lots of nice work with normal distributions. But the fact of the matter is, it isn't normal. It isn't common. In fact, a better case could be made for this curve being the normal state of play. A lot of natural phenomena do follow this curve, and it's the log normal curve. A study by Limpert, Stahl, and Abt, published in 2001, looked at a whole host of phenomena and made a good claim for log normality being more common. And what that's basically telling us is that the random effects are not combining additively, but because we're using a log distribution, they're combining multiplicatively. So that might explain why it's more common, because random effects combine more often in that way. And some of you will know that log normality is often assumed as the distribution for price returns, and that's great. But the main reason that that's done is because prices can't go below zero. So it's a way of forcing the the curve to pass through the origin. And that's all very well, but the problem is that studies of price returns have shown that they follow distributions that don't follow the central limit theorem's terms and conditions. They violate them, and there's evidence that they are neither independent, and at times of economic financial crisis, they can seem to match distributions that have infinite variances. And suddenly the normal curve isn't going to work too well just when we need it. And we end up with what are called heavy-tailed distributions. These are the ones that have infinite variance. And the classic example, the ultimate heavy-tailed distribution, is this. It's called the Cauchy distribution in red. And it sure looks a lot like the normal distribution, but it behaves very, very differently out in the tails. It has heavy tails. Now, there might not seem much of a difference between the two on that graph, but if you do the calculations, you see that the Cauchy distribution has some nasty shocks waiting for us out in the far reaches of its tails. And we can do those calculations and look at the effect of this phenomenon that the Cauchy distribution demonstrates, which is called leptokurtosis, in other words, that it's heavy-tailed. And let's compare the values that we get if we put events through the normal distribution through what we get if what those phenomena we're following is in fact a heavy-tailed distribution like the Cauchy, and just see how wrong we can be if we use the normal distribution. So let's go with a 1 in 20 risk. So an event which under the normal distribution gives us a probability of 1 in 20. With the Cauchy risk, it's 1 in 7. Oh, right. So we've been wrong by a factor of 3. Oh, that's not great, is it? Oh, just wait. Cauchy's got plenty left in its sting for us. A 1 in 100 normal risk has a 1 in 9 Cauchy risk. So we're starting to get an order of magnitude wrong now. Let's really crank it up. Let's look at some extraordinary events like 1 in a million. The Cauchy risk, astonishingly, for those events is 1 in 16. It's hardly changed. So we've underestimated the risk by over 60,000 times. A 1 in a billion risk, the Cauchy distribution, it just eats these things. 1 in 19, nothing special. So now we've underestimated the risk by a factor of 50 million. A 1 in a trillion risk, and don't forget, we're still nowhere near what Vinyal was talking about. Cauchy risk, 1 in 23. Yeah, it's just one of those things, see it all the time. And the underestimation factor is now 40 billion. Now, the Cauchy risk, admittedly, is an extreme example, and prices don't necessarily follow it. But that gives you a feel for what horrors can lie in these heavy-tailed distributions and just how wrong a normal distribution can be. So what's the remedy here? Well, we need a remedy because normality and log normality is very widely assumed in many elements of financial science, asset price returns, correlations, modern portfolio theory, options pricing model, value at risk, Gaussian copulas, which famously was the subject of a article in Wired magazine called "The Formula That Killed Wall Street," because Gaussian copulas were used to value CDOs. In fact, that's a bit of an exaggeration, and in fact, other issues were at play here, but certainly the assumption of normality didn't help things when you were estimating the risk of options going pear-shaped. So all this can be summed up by a warning from this guy, who is Paul Wilmot, who is the founder of Wilmot, which is a website for quants, which I can highly recommend, full of good stuff. He wrote prior even to the dot-com crisis, that the assumption of normality in financial science is very rarely justified, and by and large it's incorrect. It is incredibly faulty. He was saying this 20 years ago, right? Fully almost a decade before the global financial crisis hit. Unfortunately, nobody was listening. And unfortunately, not many people have moved on from the normal curve even now. But what should we be doing? Well, some remedies I would suggest is primarily to stop thinking normally and to consider, for example, extreme value distributions. These have been suggested by the Bank of International Settlements, for example, for assessing liquidity requirements, because they tend to be much more pessimistic. So banks don't like them, much more pessimistic than using normal distributions. Interesting techniques called log concave cumulative distribution function methods. I suggest looking up the paper by Faridafshin et al. 2017. Interesting bit of technique for dealing with extreme risks. And basically distribution-free bounds for assessing risk, like from Chebyshev's inequality, Cantelli's inequality, things like that, can also be useful. They're very pessimistic. They're not very sharp as bounds, but they do give you more protection because they don't assume a distribution. They just assume finite variance typically, which again is questionable, but they work most of the time much better, much more conservatively than a normal distribution. And they're less stressful as a result. So let's move on now to dangerous belief number 2, which revolves around a number. P is less than 0.05. Now, any of you who've done empirical research will be familiar with that number, because it's the number that decides whether you've got anything worth publishing or not. It's a p-value. And if you have a result that gives a p-value less than that, you've got something publishable. Now, this technique, this approach to finding out if you've got something of interest, owes its origins, and it was most promoted by this guy, the most influential and arguably the most brilliant statistician of the 20th century, Ronald Aylmer Fisher, who in 1925 brought out this book, which was the answer to so many research workers' prayers. In it, he gave basically a set of recipes for turning raw data into insight, for want of a better word. He didn't do much in the way of explaining where these methods came from, because it was intended for research workers. They're not interested in all the mathematical machinery behind it. They just want to know what are the steps required to get insight out of their findings. And its influence was massive. It became a bestseller. And it was, as far as I know, it may still be in print. It went through 9 editions during Fisher's own lifetime. And this is how it works. And some of you will be familiar with this. Basically, you conduct your experiment or trawl through a database and you collect your data. Then you calculate the p-value, which is the probability of that your finding or your theory is genuine, given, that's what that vertical bar means, the data you've seen. And then, of course, if p is less than 0.05, then it's 95% likely that your finding is genuine and that your theory is correct because it's statistically significant. But if it fails to reach that criterion, then the finding is meaningless, and it's because it's non-significant. So if you've got 3, you can celebrate your genius and you can get a paper out of it, all wonderful stuff. And if it's 4, then you'll probably break down in tears, go back to your data and keep trawling through it until you find something that does give a p-value less than 0.05. So that's what so many people do. There's just one problem with it. All of those from 2 onwards are wrong. They do not mean those things, and those are not the right way of going about things. The only thing that's correct about that recipe is the first part. So the reality is that when we're calculating p-values, no, we are not finding the probability that our theory is correct or that our finding is genuine given the data. We're actually, which is useful to know, we're actually finding this, which is the probability of finding at least as impressive data as that which we found on the assumption that the finding is in fact just a meaningless fluke. In other words, on the basis that there's nothing happening there at all, what's called the Null Hypothesis. And you're thinking, why would I be interested in that? And the reason is for a mathematical reason, but more importantly, for an emotional reason. And it stems from the fact that we can get what we want. We can get the probability of our theory being correct given the data, but not by Fisher's methods. This guy provided us with the correct methods. He was an amateur mathematician in England called Thomas Bayes, and he came up with something called Bayes' theorem, which he didn't publish in his lifetime. And he showed that the probability of our theory being right, given the data we've seen, is indeed proportional to the data that we've got, given that our theory is right. But there's a little asterisk, and that's because you have to multiply that right-hand side by what's called the prior probability. That is the probability that your theory is right before you carried out the experiment. In other words, the plausibility of the theory that you are investigating in the light of what we already know. You can't do that. You can't find out what you want to know without incorporating some idea of what the plausibility of your theory is from the outset. And that led to a huge row. Bayes never published his theorem, probably because he realized that it was going to cause a lot of trouble, because people started to think, well, that means you could say, well, I really believe my theory, so I'm going to set a very high prior probability that it's true. And so you don't need very strong data to show that, oh, look, I've proved my theory. It seemed, Bayes' theorem seemed to introduce a possibility of subjectivity into science, okay? You could just make up a prior, okay, and just plug that in to make your evidence that you then find really convincing. And Fisher hated that for psychological reasons. That was not his view of how science works. The fact that Bayes' theorem is a theorem and is therefore valid, provably valid, and is not really up for debate, and is not really up for whether you like it or not, that didn't stop him building into his book the concept that using prior knowledge is dangerous. And when he produced the book, he dismissed Bayes' theorem in one paragraph and made the book guaranteed Bayes free. And there's no mention of it in the book. And this has had a disastrous consequence for science in the 20th century. Basically because using Fisher's method, the p-value, when we find an amazing data, we just, you know, if we've got a really impressive p-value and we've got loads of data, apparently impressive data, it can just be as impressive as the data that we found. But if you use Bayes' theorem, amazing data does really well, but it's always tethered to reality, to the ground of reality by our prior knowledge. So if you do read a study, you think, really? I can't believe that. No, that makes no sense at all in the light of what we know. And I think you'll find there are some things in financial science that are like that. And you think, no, that's not plausible. And then you think, oh, well, you know, it's amazing data. Look at the p-value on it. No, you have then violated Bayes' theorem and you are heading for trouble. And you are heading, moreover, down the same route as many areas of science have now found themselves, where when they try and replicate findings based on p-values, they find they can't. In psychology, in cancer research, in economics. And statisticians in 2016 finally, almost, how many years is that? Almost 90 years after Fisher brought his book out, put a warning about the misuse of p-values, said these cannot be allowed to be continued to be used in scientific research. They are fundamentally misleading. And one of the recommendations they had is to use Bayesian techniques. And this has been noted by some very influential figures like Campbell Harvey, president of the American Finance Association, in his presidential address in 2017. He has identified exactly the same problem. This is the summary of his presidential address, which I strongly recommend you read. He pointed out that financial economics relies too much on p-values, which are poorly understood. Now, a lot of people think they're the probability of my research being valid given the data we've seen. That's not what they mean. Fisher pulled the wool over everyone's eyes there. And that rummaging around in data mining, and using p-values as the criterion for deciding whether you found something, absolutely invalid. You are guaranteed to find dross, not gold, if you do that. And it will lead to an embarrassing number of false positives. Great advice. So what should we be doing? Well, for a start, stop thinking that p less than 0.05 is a real finding, a genuine finding that shows that what's been dug out of the time series is correct, and that if it's non-significant, it's rubbish. There are many reasons why results can turn out to be statistically non-significant, but actually still valid. Believing that a value that is statistically significant is true is also catastrophic. I've recently, over the last sort of month or so, been looking at the evidence for momentum trades being successful, which is, and I've read lots of papers which have amounted to going into the famous databases, which have a whole load of empirical data, and just shifting the window for when the momentum is started and leaving different gaps, and when you form the portfolio and when you activate the all these variables have been changed. You just keep going through it. And all the ones that fail to reach significance, they're all rubbish. And the ones that are left, they must be true. Let's use those. Absolute recipe for disaster unless done very carefully. And yet it's endemic in much of the research that I've been reading of late. So that preoccupation with trawling through databases, looking for functional dependencies and deciding they're true on the basis of statistical significance, absolutely guaranteed recipe for disappointment. And what we need to start doing is using, far lower p-value thresholds. In the world of genetics, you probably remember about 20 years ago when the human genome was discovered, they said, this is fantastic. We can go through all these genes and we can link them to diseases. And that's what they did. They went through databases of thousands and thousands of genes and tried to link them to human diseases. And they found loads and loads of them. And then when they went to see if any of them stood up, no, failure after failure after failure. And then they realized that they needed to stop using 0.05 as a criterion and use a much tighter, 5 times 10 to the minus 5, or even tighter p-values. A much lower threshold weeded out so many of these false positives that Fisher's techniques can lead to. You should state your results not using p-values alone, but by giving confidence intervals, which are much more informative and allow much more information to be extracted when people try to follow them up. And you should also consider using Bayesian techniques like Bayes factors and the techniques I'm developing, which I call analysis of credibility, all available online, available to use with lots of worked examples, particularly in clinical medicine. So dangerous belief number 3, and it's about this. In other words, mistaking precision for accuracy. So let's be precise with terms here. So what do we mean by precision? Precision basically means we have a low spread. The data, yes, it's, you know, it takes on various values, but it tends to concentrate around a certain value. And we can get that by minimizing the variance. So precision in many statistics textbooks is defined as the reciprocal of variance, and you can get that by collecting lots and lots of data. That's a good way of reducing the variance. Accuracy, on the other hand, means that it actually hits the target, but if it's not very precise, it might be, you know, the data might be pretty spread out around, smeared over the target, but it's got low bias. Okay, in other words, it's not got systematic things buried in the data that are shifting it in one direction. A bit like trying to find out what the voting intentions are in the next presidential election by only interviewing people in the Republican Party. Okay, not a low bias way of doing things. Okay, and what accuracy requires, you can't really get it by analytic, you know, just collecting more data. It needs to be well-sourced data. And that often involves randomization. The only really effective way of getting rid of bias is through randomized data, which is often very difficult to achieve, as opinion pollsters know. So ideally, we like these sort of results from studies. High precision, so they're tightly clustered, so low variance, and high accuracy, so they're really hitting the bullseye. And you typically get those from large randomized studies. That's the way to get them. The randomization dealing with the bias and the sheer size dealing with the precision. Unfortunately, most studies are like this: low precision and low accuracy. That's because they're small, because studies are often designed to meet a budget rather than whether they'll find the truth, and also time constraints, and they're often non-randomized, sometimes because the data, it's not easy to get a randomized source of data, and it's very hard to apply corrections to get rid of bias. And unfortunately, most is like that. But because it's got low accuracy and low precision, the precision particularly sort of warns us that, nah, it's not very good. I think we can do better if we collect more data. And you know, it wasn't a randomized study. Let's see if we can narrow down the bias. So it encourages people to do more work, okay, which is a good thing. Now, the trouble is there are two other permutations. There's this, which is low precision. Okay, so the data's pretty spread out, but it is at least covering the target. So the studies are small, but at least they were well conducted. The data is randomized, for example, which is a very good way of doing it. And these are really good trials, really good studies, because they're the way to do exploratory studies. You couldn't afford a lot of data, okay, but at least you could afford to collect the data well. And that counts for an awful lot and encourages confidence in later studies. But we also have this. This is high precision and low accuracy. So typically a large database of non-randomized data. And this is what typically emerges from mindless big data studies, where people just wade in, make no effort to understand the origins of the data, and they end up with a very precise but very wrong conclusion. And I think that that is the most pernicious form of study, the most dangerous form of study, because high precision tends to inspire misplaced confidence in the result. Well, look, all the data was all pointed at this conclusion. It must be right. Yeah, but what about bias? What about if there's a systematic bias buried in there? very worrying because it tends to close down discussions, and we are seeing an awful lot of that in many areas of science, including financial science. So the takeaways on this false belief is that more data does not mean more reliable insights. I would point to, the existence of long time series for financial data. Data, some of it, I've seen time series going back to the 1880s even. And you're thinking, well, since about 2007, 2008, we've had quantitative easing, and that's introduced a few biases. And you have to question whether extending time series to draw conclusions about things that could be affected by quantitative easing, more data is not necessarily better data there because of biases introduced by fiscal policies. Control of random error, which is what everybody tends to focus on, what we've all been told to believe, more data is better, more data is better. It's pretty easy, especially in these days of big databases, and it tends to impress people. We looked at 1 billion data points. Hopefully, you are now starting to think along the lines of saying, yeah, so, because the more important issue is the control of bias, which is hard, but is crucial to reaching reliable insights. One quick remedy, as the genetics, the genome community found, is to impose much tougher standards. That is effectively being much tougher on random error, but in the process, because you've got a big data set, a lot of the random error is pretty much under control. It's giving you some protection against bias for free. Okay, so if you're much tougher with yourself, by setting much tougher significance levels. And I'm talking about, 10 to the minus 5, 10 to the minus 6, things that I don't think I've ever seen in any financial science study. But this is the sort of standard that's required. That can help deal with bias in non-randomized data sets. And overall, this quote is often attributed to John Maynard Keynes, but probably wasn't said by him, but it's brilliant all the same. It's better to be roughly right than precisely wrong. So to sum up, statistical methods in any field are pretty much like these. They're fantastic for digging out precious insights, like an excavator. But the thing is, they all come with guarantees that only apply if you've read the terms and conditions. Otherwise, the guarantees are invalid. And these things are very powerful, but they can be dangerous when used carelessly. So I hope that as a result of what I've said today, you'll be more minded to read the terms and conditions of any statistical technique you're using and dig carefully, and hopefully you'll find many of these. Thank you very much.
Thank you.
Okay.
Thank you, Professor Masood, for your very comprehensive and also very insightful presentation today.
Thank you.
Yes.
Thank you very much.
Yes, as a big fan of your book, I really appreciate that we having this opportunity to learn the first-hand and the direct information from you, particularly that you list 3 dangerous points. For I think that is not only very important for the researcher or the scientist, but also very important for general public. As nowadays, we got a lot of information from everywhere, Twitter, Facebook, and a lot of the social media. People also has no maybe no awareness which the information is correct or not. So I think we often saw a lot of news, the headlines say according to which scientists, and it shows maybe drinking coffee will lead the probability of having cancer. But maybe after a few years, and a lot of the research say, oh, drinking coffee can make us become healthy. So I think it's very important because sometimes lots of the news, lots of the report, maybe when it come up with as a news, even there is no citation. So maybe that could be the fake news. And even it has the citation, but we also cannot guarantee that the scientific research is robust, the methodology is robust or not. So I really appreciate that in your book, Transcending the Laws of Chance, how they can work for you. You pick up 36 example, and I think it's very important. And I think that is very good that you abstract and to sum up as very some of the key points that you introduced today. So I'm just wondering, will that be possible that you will pick up one of the example from your book and to introduce to our audience? Because I think some of our audience still have no opportunity to read your book. So I think that will be really appreciated if you can pick up one of that you think is very impressive one to introduce.
Yeah, sure. So to set some context, the book is basically in two parts. And the first part is a lot about everyday applications of probability theory and things that can help you make sense of the world around you. And then about halfway through, it becomes more about statistics and about what's gone wrong in science and gives a lot of the history to what I've talked about. And the final 2 or 3 chapters have quite a lot about finance. So your colleagues may find that particularly interesting. So I think one of the things that people find particularly interesting is the public find interesting is the phenomenon of basically coincidences, amazing things that people notice. Okay, and so one of the most famous examples of coincidences is that you only need 23 people at random in a room to have a 50-50 chance of at least 2 people in a room sharing the same birthday. Now that means that, and you can show this mathematically, that on a football pitch in any game, right, there is a 50-50 chance that at least 2 players on the pitch, if you include the referee as well, they will have the same birthday. It's absolutely extraordinary. And in fact, there is about I think it's about 90% chance that if you have 5 people in a room, just 5 people in a room, there's a chance of a shared birthday, a high chance of 2 sharing the same astrological signs, okay, of which there are 12. So you only need about 4 or 5 people to have a very good chance of 2 or more sharing the same astrological sign. So why is this the case? And the reason that it's so surprising, I mean, a lot of people, when asked how many people do you think you need in a room to get 50-50 probability that 2 share birthday, they think, well, let's think, well, there's 365 days in a year, so 50-50 chance, I don't know, 180 people, about half of 365 days in a year. And when you say it's 23, they think, whoa, how's that possible? And the thing that makes it possible, the trap that we've fallen into, is that you've not said which 2 people you want to share the coincidence. You have said that among the people in the room, you're happy for any 2 to share a birthday. Now, if you have a room of 23 people, there are 23 times 22 divided by 2, which is on the order of 250 different ways of pairing the people up in the room to make the comparison. Okay? Because you haven't said, I want at least 2 people to share the 23rd of September, say, my birthday, right? You've said, I don't care what the coincidence is. I just want there to be 2 shared birthdays. And as soon as you become sloppy and you're not bothered about specifying the coincidence, suddenly they become much more likely. And in fact, a mathematician, or it may not have been a mathematician, but somebody who knew a little bit about maths, was on a chat show in America, on the Johnny Carson show many years ago. And he said, listen, Johnny, here's an amazing mathematical fact. You know, you only need 23 people in a room for 2 to have the same birthday. And Johnny Carson said, no, that's amazing. Well, look. The studio we must have 200 people in the studio. Okay, my birthday is the, whatever it was, 5th of August. Who else has got my birthday? Nobody put their hand up. So the guy who came up with this rule was feeling a bit embarrassed and probably said something along those lines. Well, it's only 50-50. No, the mistake that had been made was allowing Johnny Carson to specify a specific day. Okay? And as soon as you do that, you need well over 200 people to get the 50-50 odds. It's much more difficult. Now, what's the takeaway from this? It's that when we see coincidences, we are very likely to be surprised by them because we have underestimated the probability, because we have not specified in advance what the coincidence is that we want to see. And as soon as we do that, the probability of seeing some coincidence of something zooms. Just think of how many potential coincidences you could specify in your meetings with the day, meetings with people during a day. Same Christian name, same first name, same colour shirt, same car. I mean, it's just a myriad of them. And you just allow any of those to count as a coincidence. So surprise, surprise, there's no surprise when one turns up. Okay, so it helps sort of people deal with superstitions about, oh, that's crazy. I was just thinking about him, and look, he turned out. Oh, that is spooky. No, it isn't. It just happens that it was just that particular set of circumstances led to that unspecified coincidence happening. It could have been something else. So I think understanding a little bit of probability can help combat misplaced beliefs in superstitions. My main concern is that understanding statistics should enable more people to be much more skeptical about what they read in the scientific journals as well.
Right. Thank you very much, Professor Masu. And I think that is also very important, I think particularly for the young generation, when they think about some romantic story. Oh my God, you are just like we have the same number or like the same birthday. I think sometimes for young people, you can also think about those romantic story in the scientific way. Perhaps you can have the new horizon and also the landscape. So thank you very much, Professor Masus, for that. So with that, I want to turn to my colleague, Professor Shaohui. So we know that you are also working on the finance and the mathematics. So would you like to share some of your feedback for Professor Masu?
Thank you, Professor Masoon. I'm quite expressed by your interesting talk. Actually, I can agree with you more that you mentioned more data does not mean more reliable insights, right? So I just want to ask you something about big data. You know that big data is becoming more and more popular, right? That all industries want to use big data for the technology innovation. But for my understanding or my own experience, I didn't feel that big data has such a big impact. For a very simple example, if you want to do some option pricing and financial engineering, the most reliable method is just the Black-Scholes model, right? So in this case, I think data is big or small has no big impact on the model, or more accurately, whether the data is big or small has no big impact on the parameter estimation of the model, right? So I'm just wondering how do you see this problem, and how do you see the big data and nowadays? Thank you.
Okay, so yeah, big data is everywhere and it is very widely used, and happily more and more people are becoming aware of the need to ask very serious questions about the origin of it. But what amazes me is that each community seems to have to discover these things themselves. Statisticians have done a very poor job of sort of communicating the fact that these problems are universal. So, the medical profession has been better, by no means perfect, but has been better on accepting some of these problems than others and dealing with them. But I still routinely see in medical journals basic mistakes in the interpretation of statistical significance, for example. Absolutely extraordinary cases, especially during the current pandemic, where a lot of what are called meta-analysis has been done, which it's like a form of big data analysis, but basically what you do is you pull together as many randomized control trials as you can to see what the overall result of pooling all those separate trials is. Okay, so this is meta-analysis. You've got lots of little trials which together have quite large variance, and you shrink the variance by just combining all the data. And then what has happened is these systematic reviews and meta-analyses have been done, and they've reached a conclusion, and they've said, but clearly this drug or this approach to protecting people from COVID infection, it does seem to have an effect. Oh, but the result is statistically non-significant even after we've combined all these studies, so it's nonsense. And that is just flat wrong. I can think of a number of cases of potential life-saving therapies and approaches to protection against COVID that are not being taken seriously because the evidence has been fundamentally misinterpreted by the medics who've done the research. So, the problems you're talking about and the problems that I'm talking about and have to address all the time, ultimately, there are two communities that need to act to solve this problem. One of them is statisticians need to stop squabbling amongst ourselves and arguing about, well, Bayes' theorem, I still don't like prior probabilities and things like that. Techniques like the ones I'm working on tackle that problem, okay? And all those sort of arguments. And the other community that needs to get its house in order are the journals who ask for academics to review papers making claims. Unless they are statisticians, chances are they'll make the same blunders as the people who did the original research. So all journals should pass papers that include a substantial amount of statistical inference in them to statisticians. To give it to anyone else is, you might as well not bother. They will just say, the chances are they'll just make the same mistake. So those are the two communities that need to put their house in order, I think. And time is running out because for every day that passes, tens of thousands more papers are coming out using these flawed methods. It's got to stop.
Yeah. Okay. Thank you very much for explanation. And Professor Masu, I actually have one more specific question. And I want to write a book on probability theory, and I'm quite impressed about a chapter which is about a relationship between uncertainty and decision making. So first, I think decision theory is one of the most important branches in economics or in statistics, or more generally in social sciences. So I'm always wondering that how do you see the relationship between decision theory and the paradox, or more specifically, the relationship between utility function and the corresponding paradox? Because you know that it is often the case that when people propose some axioms and then comes the utility function like CRRA utility, and there will always be some paradox that violate the proposed axioms. And once again, based on the paradox, people propose new axioms to substitute the previous ones, and also come with some new utility function. So people just repeat such a procedure, and it's actually from von Neumann until now, right? So I'm just wondering that in the real world, does there exist a particular kind of utility function or something like that to make people to help people make decisions completely?
Yeah,
so,
it's a very deep question and a very important question, because at the end of the day, we need to decide how we're going to act. And the basis of decision theory is that it's not just the probability of the event happening, it's also the consequences of it. And we really need to factor that in. And, again, that needs a huge amount of attention right now, because decisions are being made where just on the basis of probabilities, not taking into account the impact, the consequences of these high or low probability events. It's a huge subject. I only wish we had more time to discuss it.
Thank you very much. So Hongyi, I didn't have more questions,
no problem.
Okay. So thank you very much, Professor Masu. So here is a selected question from the audience. So the audience would like to know, given you mentioned the big data in your presentation, and as we know nowadays, a lot of financial technology company or the banking sector, they are adopting the big data and also artificial intelligence to build up the model and to use the machine to decide whether to approve the loan application or not. So how do you think on that? Will that lead our society in an efficient way, or will that also create more bias, as that you mentioned in your presentation? And how do you think about that? We will very much like to get your perspective on that.
Again, a huge subject, absolutely fascinating subject, and it's starting to attract the interest of the legal profession. Lawyers are getting interested in this. And for example, the European data protection regulations, general data protection regulation, GDPR, actually says that, if you are reaching decisions on the basis of things like neural networks, artificial intelligence, you must be able to justify, give a plain language justification of why the artificial intelligence reached the decision it did. And this is very, very scary from the point of view of neural networks are trained on the basis of large data sets. If the data sets contain bias, and someone who's been turned down for credit can show that, oh, I'm from a minority group, and I wasn't represented properly in the database, there will be legal action. There is the potential for legal action now. So this is no longer just a computer science issue and an issue of fairness and ethics. This is rapidly becoming a legal issue and must be addressed. And it is very tricky to do. Yeah, people are working on it, but I can't believe we've got as far as we have before, this is being addressed. We need techniques to address the explicability problem. In other words, why did the neural network, why did the artificial intelligence reach the decision it did? So, and to show that it's not based on bias. Lots of problems there. Fascinating area of research.
Right. Thank you very much, Professor Masu. And I think today we really learned a lot of information from you and very insightful. And I think that is very important lesson that everybody should take, given nowadays a lot of information. And when people want to anti-fake news, I think maybe on one hand side that government should take some action, but on the other hand side, the most important thing is that we can take those of the tool and the methodology you introduced today into consideration, and to build up your own critical thinking and to justify which one will be reliable and which one we should be still skeptical with that. So really appreciate for your time, valuable time today, and we hope to see you again either online or maybe in Hangzhou, or maybe in London in the near future.
I look forward to it. Thank you very much.
Right. So before we close in that, I also want to appreciate Professor Masus and also Professor Shaohui once again, given today we have a lot of audience, 12,000 people, online audience following us in China today. So really appreciate for making this happen.
Thank you.
Thank you,
Hongyi. Thank you.
So have a nice day, Professor Masu.
Thank you very much, and you, and to everyone out there.
Okay, stay in touch. Bye.
Bye-bye. Bye-bye.
Bye-bye.